Addressing compressor issues following an ice storm necessitates a methodical troubleshooting process. The initial step involves checking for short circuits within the wiring or the compressor windings. Employ a multimeter to assess continuity between the compressor terminals and the ground. The absence of continuity indicates a potential short circuit. The next step includes an inspection for loose or damaged connections. Secure all electrical connections, ensuring they are clean and devoid of corrosion. A loose connection can cause arcing, which results in breaker trips. Testing the compressor capacitor is crucial. A malfunctioning capacitor may lead to excessive starting current, subsequently tripping the breaker. Employ a capacitor tester or multimeter with capacitance measurement capabilities to ascertain the capacitor's health. Also, confirm that the correct voltage is being supplied to the compressor. Insufficient voltage can induce the compressor to draw increased current, triggering the breaker. Use a voltmeter to measure the voltage of the compressor terminals under load conditions. Now consider the second compressor and the situation where the 200 amp breaker is tripping. Conduct a comprehensive check for ground faults in the compressor windings or wiring. Utilize a megger, also known as a megameter, to evaluate insulation resistance between the compressor and the ground. Reduced insulation resistance signals a potential ground fault. Inspect the electrical panel meticulously for loose or damaged connections, particularly in proximity to the 200 amp breaker. Tighten any loose connections and replace damaged components. Test the main feeder cables and other circuit breakers within the panel to ensure their proper functionality. Employ a multimeter or circuit breaker tester for this purpose. Be aware of the possibility of a neutral to ground fault within the electrical system. This phenomenon can cause neutral current to reroute through the ground wire, ultimately tripping the main breaker. Utilize the multimeter to measure the voltage between the neutral and ground wires. An elevated voltage signifies a potential fault. Now, shifting focus to the third compressor, which exhibits a locked rotor condition. Examine the compressor for excessive mechanical resistance, such as a seized bearing or a bent shaft. Attempt manually rotating the compressor shaft to ascertain if it is seized. Inspect the compressor meticulously for any visible damage or leaks. Signs of damage or leaks may indicate internal mechanical failure. Test the compressor's starting relay and overload protector. A defective relay or overload can trigger the compressor to draw excessive current during startup. Employ a multimeter to assess the relay and overload protector's functionality. Moreover, consider other crucial factors. Inspect the system's refrigerant charge. Insufficient refrigerant can lead to compressor overheating and subsequent failure. Utilize pressure gauges to evaluate the refrigerant charge level. Inspect air filters and coils for any obstructions. Restricted airflow can also contribute to compressor failure. Clean or replace air filters and coils as necessary. Verify if any modifications or upgrades have been implemented in the system recently, as these could have introduced potential issues. Analyze wiring diagrams and consult with technicians to ascertain any recent changes. Contemplate the possibility of lightning or power surge damage during the ice storm. Examine for any indications of burnt or damaged electrical components. Utilize a multimeter to evaluate component functionality and check for signs of damage. Should the issue persist or further investigation be warranted, consult with a qualified electrical engineer. An electrical engineer can offer specialized expertise and conduct comprehensive system analysis. Always prioritize safety during troubleshooting. To energize the circuit prior to conducting any electrical tests. When working with electrical components, use appropriate personal protective equipment, which includes safety glasses, gloves, and insulated tools. Additionally, it is important to understand the basics of electrical circuits, wiring, and components. Comprehending the fundamentals facilitates more effective troubleshooting. Breakers trip due to overcurrent, short circuits, or ground faults. An overcurrent is when the current exceeds the breaker's rated capacity. A short circuit is an unintended low resistance path that causes a large current flow. A ground fault is when current flows through an unintended path to ground. Compressors require proper voltage and current to operate efficiently. Low voltage can cause motors to overheat and draw more current. Locked rotors can cause excessive current draw, leading to thermal overload and breakout trips. Refrigerant is essential for cooling and lubrication in compressors. Low refrigerant charge can cause overheating, reduced cooling capacity, and compressor damage. Airflow is crucial for heat exchange in HVAC systems. Restricted airflow can cause overheating, reduced efficiency, and compressor failure. Electrical connections must be tight and free of corrosion to ensure good conductivity. Loose or corroded connections can cause arcing, overheating, and voltage drops. The neutral wire carries the return current from the load back to the source. A neutral to ground fault creates an unintended path for current to flow through the ground wire. A megger is used to measure insulation resistance. Low insulation resistance indicates a potential ground fault. Overload protectors are designed to protect motors from overheating due to overcurrent conditions. Starting relays are used to provide a temporary boost of current to start a motor. Capacitors are used to improve the power factor and reduce the current draw of motors. Ice storms can cause power outages and surges, which can damage electrical equipment. Always energize circuits before working on them to avoid electrical shock. Follow all safety precautions when working with electricity. Consider the age of the equipment. Older equipment is more prone to failure. Regular maintenance can help prevent equipment failures. Keep accurate records of all maintenance and repairs. Use appropriate tools and equipment for the job. If you are not comfortable working with electricity, hire a qualified electrician. When replacing components, use the correct replacement parts. Consult with the manufacturer's specifications for the correct voltage, current, and refrigerant charge. Check the wiring diagram for proper connections. Always test the system after making repairs to ensure it is working properly. Consider using a surge protector to protect the equipment from future power surges. Ensure adequate ventilation around the equipment. Keep the equipment clean and free of debris. Check the equipment regularly for signs of wear and tear. Address any issues promptly to prevent further damage. Document all troubleshooting steps and findings. This will help with future troubleshooting. Use a systematic approach to troubleshooting. Start with the simplest possible causes and work your way up to the more complex ones. If you are unsure about something, ask for help from a qualified professional.